Hi everyone, I'm Matheus, a PhD student at Zurich, and today I will continue this session about vector processors, talking and updating about the status of ARA, the vector processor that we've been developing back at ETH based on RISC-V's vector extension. To give you a bit of motivation about why we developed this, I bring up Ariane, which, for example, Rick O'Connor this morning discussed about it on his Core 5 presentation. Ariane is our RV64GC core. At the F23, it works at 1 gigahertz. And we were thinking about how to push Ariane further to have higher performance. And that's the idea behind ARA, which is tightly coupled to Ariane, even though the interface is quite lightweight, it's just the instruction queue and this acknowledgement path. We also made sure to enlarge, to have a wider memory interface with ARA, so that it could serve all this high performance that it requires. To analyze performance of Ariane, I will constantly bring up this graph, which is the roofline path, the roofline plot, which shows us the maximum achievable performance of a core of a system as a function of the arithmetic intensity. What is the arithmetic intensity? It's a measure, in a way, of the data reuse of an algorithm. It's algorithm dependent. It's not, for example, it does not depend on the core itself. In this measure, I'm considering that one FMA is 2 operations. In this plot, at the right side of the screen, there are the maximum achievable performance for several ARA instances, and there are 2 regions in this plot. The compute-bound region, which is where the performance of ARA or of any core actually is limited by its computing units. But there is also the memory-bound region, which is the region where the processor is being limited, is waiting for memory. It cannot achieve its maximum achievable performance. It cannot have a high utilization because it's being starved waiting for memory. The transition between those 2 regimes is defined by the ratio between the peak performance and the memory bandwidth of the system. For ARA, for all instances, we are considering this ratio to be at 0.5 gigaflops per byte, which means that the memory bandwidth is actually scaling with the number of lanes. So ARA, its implementation was on GlobalFoundries and 2FDX process. It was a work that I started during my master thesis last year and was first presented on the summit last year in December. And for more details, there is this paper at arXiv that you can look at. So ARA was based at the RISC-V vector extension, as I said briefly during the start of my presentation. And this extension is a Cray-like vector processing, as opposed to opaque SMD, which is the approach taken, for example, by the DSP extension, RISC-V-P, or ARM Neon or Intel Multimedia extensions. In this Cray-like vector processing, you actually have a vector instruction that encodes a certain number of vector micro-operations, so that the execution part of your instruction actually takes longer than the fetch or decode parts, so that you are not spending energy and time at this part. You're not wasting energy there. ARA is not based on the latest version of the RISC-V. It's actually based on the version 0.5, even though there is work being done back at ETH to update it to the latest version. And this is why we say that the open sourcing will be done by the first quarter of the next year. In terms of state of the art, I mean, I'm the 3rd presentation at this session about vector implementations. But there are quite a few during the summit, but also some academic, for example, Huasha, which is based on the custom RISC-V extension. Other commercial vector processors which are not RISC-V vector-based. For example, Fujitsu's A640FX, this being based on ARM's take on Cray-like processing, ARM-SVE, and some mixed approaches. Back in Europe, there is this European Project Initiative, EPI, which plans to integrate a vector processor inside its EPEC tile. This vector processor being also based on the RISC-V vector extension. So after this introduction to my talk, I will dive into the microarchitecture of ARA. I will try to do a bottom-up approach. So we will start with the main data path elements. I will start with the computing units. So per lane, we have 3 of them: the integer ALU, the integer multiplier, and the FPU. And what's interesting about them is that they all have a throughput of 64 bits per cycle, regardless of the vector of the data representation being used. What this means is that we, inside the lane, we have something which is closer to a PAX SMD approach. Speaking of the FPU, for example, what this means is that this FPU supports FP64, 32, FP16, but also bfloat 16. We have different pipelines, different independent pipelines for each one of those data representations, each one with a different latency to meet our timing constraints. And for example, if you are working with FP32, you will produce 2 elements per cycle to achieve this 64 bits per cycle throughput. So one level higher, instead of talking about the functional units, let's talk about the lanes. So we have one vector REST file per lane. We try to make the functional units, the lanes itself, the most independent possible. Our vector REST file, it's composed by 8 SRAM banks, each one 64 bits wide, so that the functional unit on access its own section of the REST file. Because of this configuration, this means that the vector REST file requires some arbitration. For example, when 2 functional units are trying to access the same bank. In order to be able to hide the latency and hide those bank conflicts, we have those, what we call those operand queues that store elements that will be used by the functional units. We have one FIFO per operand per data path unit, or 10 queues. And we have the equivalent queues on the output. I highlight here that there are 3 queues in this diagram that are not connected to any functional units inside the lane. Those queues, they are in this case, for the load store unit, for units that need to access data inside all lanes. So this is how the top level diagram of ARA. At the top of this diagram, that is how the instructions they arrive at ARA. They are forked from Ariane's issue stage. It's a very simple forking. As soon as Ariane finds that you have a vector extension, it sends it to ARA. And all the bookkeeping, all the organization, all the issuing of those vector instructions to the different functional units, to the lanes or to the lanes, is done by this sequencer. And as I was referring before, you have some special units that need to access all lanes. For example, the load store unit, you need to write to all lanes, and also the slide unit. And as we will see later in my presentation, this will actually be the scalability issue, the Achilles heel of the algorithm, of the implementation. About the load store unit, it has a width that scales with the number of lanes. So the width of this XI interface is 32n in order to keep the performance per bandwidth ratio at the level that we said before. So now let's discuss performance. I chose to bring up at my talk here just one benchmark, the matrix multiplication, double precision, and by n times n, the algorithm is doing this operation. C receives A times B plus C. In terms of arithmetic intensity of this algorithm, we have 32n square bytes of memory transfers at minimum to do this algorithm, and 2n cube operations. What this means is that in terms of the arithmetic intensity, we have n over 16 flops per byte. And this implies that as soon as n is larger than 8, we should be in the compute boundary regime back at the roof-line plot of the beginning of my presentation. This is, we should be able to achieve the maximum possible the peak performance of ARA. So here at this diagram, there are a few points at the right side of the screen which show the achieved performance for 2, 4, 8, 16 lanes for this n size of the matrix multiplication. We do achieve a very high efficiency, a very high utilization of the functional units. Here we are 2 or 3% below the peak performance of the design for a wide range of number of lanes. However, we cannot always achieve this performance. We do see a certain performance degradation once when we have smaller matrices. However, well, as I was saying before, we should be able, from the roofline plot, to achieve the peak performance even at those smaller matrices. But it's almost as if there was an extra boundary here that is not exactly memory, but I don't know what it is, that is limiting performance. To understand what is happening here, we need to dive a bit deeper into the matrix multiplication implementation. So how it works. The standard way to implement a matrix multiplication is slow, like taking a row and a column, multiplying them, and then reducing. Mainly because the reduction is slow. If you want to be IEEE compliant, you need to do this reduction sequentially. It doesn't work. We have another approach, which is using a vector of reductions. This is actually a very standard implementation of the matrix multiplication for vectors. How we do it? Let's say, take this small example, a 4x4 matrix multiplication. First step, we load one element of the matrix A, one element, and we broadcast, we splat this element into a vector, in ARA. In this case, VA. Doesn't matter which vector, but we splat it. Second step, we load one row of the matrix B in another vector register. And then we do a multiply accumulation. We accumulate this result into VC. Next step, we load another element of the matrix A, we splat, same thing. We load the next row of the matrix B, and we accumulate in the same vector. And when we do this operation, this iteration to all the elements, to the whole row of the matrix A and all the rows of the matrix B, we will finally have one row of the multiplication between A and B. How this maps in assembly code? So first we have one vector load. We load one matrix into VB. Then we have one loop, but we unroll this loop to avoid any extra branching or stuff like this. We load one element of the matrix A. We do this, and in Ariane's side, we do a scalar load. And then we bump the pointer we prepare to the next iteration. We broadcast this element that we loaded in Ariane's side to ARA. Back at the time at the version 0.5 of the vector extension, that was the way to do so. And then we do the multiply accumulation. And then we repeat the same 4 instructions as many times as needed. What this means is that we have these 4 instructions they repeat, which means that we are issuing a vector multiply accumulation at best every 4 cycles. Because first, Ariane is single issue, and we have 4 instructions between the multipliers. And what this implies is that if the vector instruction executes too fast, if you have too many lanes in small matrices, ARA or the vector processor or anything really will starve, not waiting for memory, but waiting for instructions. And this is actually the von Neumann bottleneck, which is very interesting to see it appearing here in a vector processor, which is something that was in a way conceived to avoid the von Neumann bottleneck. And there is a little some math in the paper that we published that shows that this issue rate translates to this boundary in the roofline plot. And taking into account this boundary, we do see that the performance achieved by ARA do follow those boundaries. Now, to finish my presentation, I will discuss a bit about the physical implementation. Here at the screen, we have the 4 lanes instance of ARA in 22 FDX. Nominal typical corner with some body biasing to do some corner trimming. We achieve 125 gigahertz. In terms of area, some figures of merit of this 4-lane implementation. The area is roughly dominated by the lanes themselves, and the area of the lanes is dominated by the functional units and the vector raster file, which is good. We are not wasting area on the control. Like, it's what you expect of a vector processor. In terms of performance, taking this 256 by 256 matrix multiplication that I was discussing before, we achieve about 10 gigaflops at 260 milliwatts, which implies an efficiency of 38 gigaflops per watt. But we were able to scale ARA all the way up to 16 lanes. Those are the final backend results. And then that's where we start to see those performance, this scalability problem that I was hinting at the beginning of my presentation, which is you have all those 16 almost independent lanes which concentrate and need to communicate at the slide unit and the load store unit. And this is why in the timing reports I saw that this is what was creating some timing degradation of those lanes. So with 16 lanes we achieve basically 1 gigahertz on the nominal corner, 32 gigaflops with the same matrix multiplication. Which implies an energy efficiency of 41 gigaflops per watt. To conclude my presentation, some final remarks, a bit of discussion. It's something that was, in a way, not forgot, but we stopped discussing about this in the vector extension, was going behind the 1D vector processing and having some kind of 2D vector instructions. This was basic because the vector extension as is already very large, is already, namely, I would say, the most complex extension of RISC-V, and there is probably no encoding space to include those 2D shapes. But they might become interesting in this case because if we come back to my matrix multiplication example, we had an n by n matrices, but we were operating on rows of length n. If we had some kind of magic instruction that instead of operating on those rows, they operate on matrices, on small matrices, it would alleviate a bit the von Neumann bottleneck, and we could hopefully achieve a higher performance at those smaller matrices. But then we have a question, is it worth the hassle? Is it worth the hassle of updating and adding those 2D instructions to the ISA just to have better performance at something that it seems that the vector processor, the whole architecture was not built for? Something that I don't think the matrix multiplication itself can answer. Is something that maybe would require some more benchmark analysis, as I would say. So there are more details on ARA on its TVLSI paper. Here is its DOI. As I said in the beginning of my presentation, the open sourcing will be done from within the POP platform, and please feel free to contact me at my mail. And thank you. So if you have any questions.
Did you look at the GitHub of vector spec? There's a better implementation of matrix multiply. You know, you'll get better performance if you use this open source code.
Actually, the implementation that is in the spec is very similar to this. Namely, I think the adding of an extra instruction in the newest iterations of the ISA made you, instead of having a loop which is 4 instructions long, it's 3 instructions long. So this might alleviate a bit the issue. To see if the microarchitecture of the scalar core allows you to issue the vector multiplier accumulation, the vector FMAs every 3 cycles. But the thing is, it doesn't really change the problem itself. If it's 4, 3, 5 cycles, that boundary that I showed in my roofline plot is just shifted.
Yes, this is a very good academic research project, but I actually question the feasibility of using 2D native operations, just because the way memory is accessed is typically 1D. You would have to build some sort of way to access memory in a 2-dimensional fashion in order to be able to get the bandwidth in order to feed something like this in a single instruction machine. You simply may just need to increase the issue with, to match, whatever it is, the structures. You would need at least an extra instruction for a memory fetch and an extra slot for the actual computation. With a 1-issue machine, you may be getting slightly misleading results. I think probably you'd want to go at least to a 2-issue machine to be able to see if that would optimize it better. But otherwise, very good. Thank you.
Thank you. Yeah, and I totally agree. I mean, was a bit the same answer for the previous question. If you have a double-issue machine, you would be able to issue your vector, this FMA instruction, twice as fast. This would shift the boundary, but the issue is still there. You just have a more complex core driving your vector unit. But I do agree. Yeah, something that we might check later, but the thing is, with the ISA as is, we are able to achieve a very high utilization on the larger matrices. Those are all optimizations for the small stuff, which is it worth it? Like, it's a question that I leave for you. So, thank you.